You hit record? Okay, good. I'll begin. Dear Father, we thank you for this day again, Lord. We thank you for the weekend, time to relax and refresh. Just pray you be with us today. Help us to, again, Lord, just to glorify you. And we do, Lord. In your name I pray. Amen. Okay, so I want to just talk about what's called Taylor's theorem. So we've done some of these calculations before, like if we wanted to find a polynomial which fit the value of a function at a and its derivative at a, then the natural choice is to make the constant the value of the function and the coefficient of x minus a to be the derivative, right? And then if you want the best quadratic approximation, well, you just keep doing this, right? You go and if you work it out and set the quadratic, we want the quadratic to match the function at value, its first derivative and its second derivative. That leads you to this, which is just a little bit beyond the tangent approximation. This is the best quadratic to approximate the function near the point. And then you can go on and you can find the best cubic approximation, right? Great. And so in general, we defined this the other day. The kth Taylor polynomial is just going to be the sum. Basically, we start with the linearization. If we set y equals this stuff, we get the tangent line through a comma f of a. And this is just not the Taylor series, right? But the Taylor polynomial up to order k is what this is for the function f centered at a. And so I have a few examples, a few visualizations here, just showing you how it works. So here's the exponential, and I find the first few Taylor polynomials centered at -1. It's easy enough to calculate derivatives of the exponential. And so there you go. There's the 0th, the first, the second, the third Taylor polynomials all centered at -1. And I've even got them graphed over here. So the red line is the exponential. This is the tangent line to the exponential at -1. Here's the best quadratic approximation, right? The best cubic approximation is this purple curve, right? And then the best quartic, I think I might even have graphed. No, I don't. But as you can see, the cubic stays close to the line, rather stays close to the red the farthest, right? If you look at it, you can only see the cubic lifting off the actual graph of the function, like here and over there. On the other hand, you can see the quadratic approximation separating from the function, like back here even, right? So the higher order terms we take, the closer we get to the function, the longer is just the basic concept here. In other words, higher order polynomials give you more flexibility to fit functions. Here's another one. The first few Taylor polynomials for 1 over x minus 2 plus 1. So I calculate some derivatives. And here's the first, second, and third Taylor polynomials centered at 1. For the function. The function I've graphed in red, and as you can see, the tangent line does, it's okay. The quadratic sticks with the function a little bit longer, but the cubic even longer still, right? And yeah, as you can see, the function itself has this vertical asymptote. It doesn't matter how high we go, we're not going to be able to cross that vertical asymptote with the approximating polynomials. So this is leading to a question, which is, how many polynomials do you have to take to approximate a function to within a certain tolerance, right? Like if I need a model of my function to be within 1% of the true, like the true function. If I need to, when taking a function, I'm replacing it with some sort of polynomial approximation of the function. How many terms in the polynomial do I have to take in order to model the function within a certain precision? This is a question that you'd like to answer, right? I mean, because if you're going to use this as an approximating procedure, you need some kind of precision. Here's another example. This is actually the graph of sine is red, and it's kind of hard to see, but of course the tangent line is the blue one. We use that in physics all the time. Sine of x is approximately x from about plus or minus 20 degrees to within 1%. But if you wanted to get better, you could take the cubic approximation, which I've got green. As you can see, that sticks pretty close to sine. Looks like almost all the way to 90 degrees, plus or minus. And then if you want to get past that, we'll take higher order approximations, like this is probably the 5th order one, it's probably the purple one there. And I'm guessing the yellow one's maybe the 7th order approximation to sine. I forget what I have written here somewhere, but if you go high enough, you can keep tracking sine further and further away from the origin, right? So how far you want to track sine depends on what you're doing, right? If you're just working a problem in physics where you're just approximating small angles, then sine of x equals to x is like pretty good. But if you want your model to replicate sine for a couple of cycles, then you probably need to work with a higher order polynomial, right? Here's another one. Relativistic energy is, you've heard it's m naught c squared. That's a lie. It's actually m naught c squared over the square root of 1 minus v squared over c squared, where c is the speed of light. This is the true relativistic energy as a function of the velocity of the particle, the speed of light, and its rest mass m naught. So if you calculate the derivative of that, you get this. And so after a little bit more calculation, you'll find out the fourth derivative ends up giving you this coefficient. So this is the Taylor polynomial in the relativistic energy up to order 4. So there's the rest energy. That's your 0th order term. If you studied physics, you could recognize this. This is what? Kinetic energy, classical kinetic energy. And then here's the thing that we don't talk about. That's the correction, the next thing up in the power series for the energy. So this was actually surprising because, well, that's kind of shocking and actually appreciable. This we've done a fair amount of physics with. North Korea is still doing it out in the open or underground. I don't know. Whatever. You go to North Korea, you figure it out. But where was I? So here's the picture. The classical kinetic energy is in green. You can have speed arbitrarily high, positive or negative in principle, well, velocity rather, for classical physics. But in relativistic physics, if you look at the formula, which is on the previous slide, for relativistic energy, it actually only makes sense for velocities between plus or minus c. And this is a graph of the relativistic energy. And there, as you can see, relativistic energy is really close to classical kinetic energy, provided you just ignore this piece right here. Yeah. Now, one of the fascinating things, this is more a point of philosophy than anything else, but is physics is for some reason so construed to allow us to study different energy regions separately. Like we could meaningfully study classical mechanics, right? The physics of fairly slow moving stuff that's not too massive, and we got pretty good at that in the 19th century, and that's really interesting because later we learned that there's this thing called special relativity, which covers the same territory, right, but at a different energy regime, and it just so happens that special relativistic effects don't interfere with classical mechanics. So we could study classical mechanics without knowing anything about special relativity, right? And that's really very, very fortunate for us from a naturalistic viewpoint. Now, from a Christian viewpoint, I don't think it's surprising at all. God has constructed the universe in such a way that we can understand it piece by piece. I mean, that's part of His providence, to break nature into pieces that we can understand bit by bit. But this is a mystery to the naturalists, the fact that physics is decoupled, that we can understand it step by step. Anyway, there's multiple universes. There's this anthropic principle and all kinds of stuff you'll learn. But if you like that kind of stuff. But I'm digressing from math slightly. But I would ask you kindly remember this on the worldview question of the course evaluation. Thank you. Okay, so sorry, I'm being an idiot. I'll stop being an idiot at some point. Okay, finally, what we're talking about today mostly. Not really. This is just a passing thing. But this is Taylor's theorem with Lagrange's form of the remainder. Suppose you got a function. It has k derivatives on a closed interval I, and the boundary of I is a to b. So what I'm saying is a is either a to b or it's b to a. I mean, one comes first or the other. But so if you like, you can just set I equals to a comma b if that would make you feel more comfortable. And this is the boundary. This is the edge of the interval. A and b are the edge interval. Then this is just the definition. F of b would be the kth Taylor polynomial at b plus the remainder of the kth Taylor polynomial be? How do you define the remainder? The definition of this is just that it's this minus that. Okay, so it's not, well, anyway. Actually, that might be a lie. Well, anyway, let's go on. So the point here is that this is by definition the kth Taylor polynomial. That's the remainder term. And this is what Taylor's theorem says. Taylor's theorem says that there exists some c which is in the interior of the interval such that the remainder at b can be written as the k plus 1th derivative evaluated at this c divided by k plus 1 factorial times b minus a to the k plus 1. So does this I don't know if this reminds you of anything, maybe, maybe not. But in Calculus 1, we talk about the mean value theorem, right? And so the lowest order version of this, 666, which is incidentally also the page in your book, which, oh man, that's funny. You know what page, you know what's on page 466 of your book? I mean 666 of your book? Tell us, Josh, what's on page 666 of the book? What's going on?
No, on page 666 of the book is convergence of Taylor series.
That's what this.
On page 642.
But this is actually what we need for convergence of Taylor series. So it's not.
But the theorem itself is on page 642.
Don't rain on my parade. It's mystic. No, I'm digressing. Okay, so to prove this, which I think you should at least see, if not write down. What you do is you construct a function g by f of b minus this stuff. Now, the way I've constructed this is so that this is a differentiable function because it's built with the function and up to its k minus 1th derivative. We're assuming that the function is k times differentiable, so we can definitely differentiate this thing. It's differentiable. It's a differentiable function. And it's continuous because, very, very similar comment. But more than that, you can calculate what's g of b. Well, if you put in b, you get, what happens here? 0, 0, 0, f of, it's 0, all right? G of b is 0. And what is g of a? The definition of m that I gave, it says g of a is equal to 0. So we have a differentiable function that's continuous, and its values are 0 at a and b. Therefore, by Rolle's theorem, which you may remember, or you may not from Calculus 1, there exists c such that g prime of c is 0. And then if you actually calculate the derivative of g, which is this, all right, and you plug in this c, g prime of c being 0, what happens? So you have this c such that g prime of c is 0. That means if I plug in c here, this minus that has to be equal to 0, all right? But what does that mean about the k plus 1, the k plus 1th derivative, kth derivative, excuse me, at 0? So it tells me that m is equal to the kth derivative at c. Let me go back here and show you what m was. I defined m according to this formula right here. So I actually, it's the next thing beyond the k minus 1th Taylor polynomial. This goes back to accounting thing. Sometimes I call the kth, if you say this is the first one, then that's the second one, right? Then this would actually be the kth one. Depends on how you count, right? If this is the 0th one and that's the first one, then this is the k minus 1th one. What I have done in here, though, is to say the kth order Taylor polynomial has up to terms order k. So let's just stick with that terminology if it's all right with you guys. Like the second Taylor polynomial goes to order 2. If you want to be fussy, it's actually the third one because you could have a constant, a linear one, or a quadratic one. That's the third if you're counting. But if we count from 0, it's the second. Yep.
So if we're asked to find like the 4th order polynomial, that would really be like k is equal to 3. because that has.
No, if the fourth order, if I say fourth order polynomial, it's up to order 4. But if I said the fourth Taylor polynomial, in this way of counting it would just be to order 3. If in doubt, ask me. Okay, I don't think this is going to actually be a point of confusion. The larger point here, though, is that this m we just worked out is like f prime of c. And this is exactly the remainder term, so that proves the theorem. So in short, I mean, you can study this more carefully. And the essential result here is that the part that remains in the Taylor series for a function can be, or the part past the kth order Taylor polynomial can be given by a k plus 1th derivative evaluated at some point c in the interval. That's what Taylor's theorem tells us. So it means that we can understand how a Taylor polynomial is approximating a function by looking at the next term we haven't used. This sounds very familiar, right? This is almost the alternating series estimation theorem, but it's not quite that simple. Anyway, here's the actual bound that we can use if we have a k plus 1th continuous differentiable function on interval pq. Let's say it has length L. And let's suppose that the k plus 1th derivative is bounded. So we have m as like an upper estimate for it. Then the remainder term, this is the error between the function and the kth Taylor polynomial, is at most m L to the k plus 1 over k plus 1 factorial. So in particular, this shows that if you can show that an arbitrary derivative of a function is bounded by some m, like a fixed constant, then it follows that the remainder must go to 0, because as k goes to infinity, this gets super huge no matter what L is, right? So we've almost, so from that discussion, you can see why like the series for sine, what's the bound on the k plus 1th derivative for sine or cosine? Derivatives of sine or cosine are what? Plus or minus sine or cosine, right? What bounds those? The absolute value of sine or cosine is always less than what? 1, right? So you could, for sine or cosine, this m you could just take to be 1. So this theorem would then show us that the sine or the cosine series necessarily converges and in fact approximates the sine or cosine functions for arbitrary real numbers. I actually go a little bit further here, and I estimate, here's just some toy examples. This is a 5th order polynomial, and I calculate the second derivative, and I find that the second derivative is this, and so like f of 0 is minus 60. My question then is, if I use the second order polynomial, t2, is it a good approximation for f of x? Well, how bad is that? Well, if you look at the third derivative, we get this, and the fourth derivative is that. And so if I look at minus 1 to 1, minus 0.1 to 0.1, then you can see that the fourth derivative is positive there, right? So it's increasing. And what does that say? If the fourth derivative is positive from minus 1 to 1, that means that the third derivative is a strictly increasing function, which means that we have the third derivative at minus 1 is less than the third derivative at x is less than the third derivative at 0.1, because the third derivative is increasing, right? So it preserves inequalities. Then this tells me that if I look at that, I've got this less than the third derivative less than that, which tells me 92.4 is less than the third derivative is less than minus 20.4. That allows me to bound the third derivative. The third derivative is bounded by what? 92.4, in fact. See, because it's between minus 92.4 and plus 92.4, by the way. So there's my bound on my third derivative. So going back to the error estimation, I get my delta. That I used L in the theorem rather than delta, but that is playing the role little L did in the theorem I had up a second ago. And so working it out, I get 0.123. So what I did was I illustrated this 0.123 error band around the quadratic polynomial, which is approximating this 5th order polynomial. I'm actually visualizing. Here's a visualization of that error approximation. So what you're looking at here, this is the quadratic, which is approximating this wild quintic, right, close to that point. And this is the tolerance given to me by Lagrange's form of the remainder as I've worked it out. As you can see, I haven't done a super good job working out the error. my error is like much bigger than it needs to be, right? You can see it. I could have been a lot stingier with the error, right? And but as you can see, it's at least true that the approximating green curve is within the tolerance illustrated by the gray, and that's the model. So if you actually want to work out details, you've got to work out what's a bound on the next term you're not using over the whole interval you're looking at. That's how we get it. I have another example. How about sine x? Sine x on the interval -1 to 1, right? Or -2 to 2. So, of course, the bound on the nth derivative of sine is 1, like I was just talking about a second ago. And so if I want the error to be less than 0.1, for example, on -1 to 1, then I need to look at, so that the length here is 2, so 2 to the k plus 1 over that, less than 1. So how do you solve something like this? How do you solve 2 to the k plus 1 over k plus 1 factorial less than or equal to 0.1? You don't solve for k, right? You just start looking at values one after the other. We were talking about this, Josh. You're like, how do I solve something like this? You don't solve it. You just start probing numerically until you find the first place that you win. So if I look at E1, the error, if I just take the first one, that's not good enough. 4/3, not good enough. 2/3, not good enough. Third, still not good enough. By the time I get to the fifth term, 64 over 720, well, that's 0.1, so woohoo. So apparently, if I take the fourth order Taylor polynomial, then that'll be enough. But in fact, T4 is equal to T3 because the fourth order term vanishes for sine. And so this is the third. This will be within 0.1 over the interval I'm looking at, which I believe was -1 to 1. And here's a picture of it working. So what you're looking at is the actual sine function is in red. This is the cubic approximation to sine, and there's a picture of the error bound I just worked out. And as you can see, it fits within the, well, I mean, that's the plus or minus 1 tolerance. As you can see, it actually works again. I've got one or two more of these. I'll show you the one I'm interested in. Oops. Let me zoom out a bit. Here's actually a picture showing you that sine x is equal to x within 0.01 for that far. There's a picture of it actually happening. And here's the analysis, which proves that will happen on the basis of Lagrange's form of the remainder. Here's a more interesting example. So all the time in physics, we tell you two things that seem at odds with each other. On the one hand, we tell you F is equal to mg. But on the other hand, we tell you F is equal to minus gmm over r squared. So which is it? Is there a universal law of gravitation, or is F equal to mg? Like, how can you have both at the same time? What is F equals to mg? That is the 0th order approximation to the gmm over r squared equation. And this r is actually the radius of the Earth plus the altitude. Right? So when you use the force of gravity as mg, you're making a approximation. You're not even doing linearization of gravity. You're replacing it as a constant. And this approximation, F equals to mg, it's only legitimate as long as your altitude's about 0. If your altitude gets too big, then it's no longer valid. This mathematics that I'm about to describe explains quantitatively how far you are in error. So this is the force of gravity as a function of altitude. Its derivative is this. So it's clear that the second derivative is negative, means that the first derivative is decreasing. So I have that if 0 is less than the maximum altitude, then that gives me a bound. Anyway, here, let me get to the point. So here, after a little bit of calculations, I come to the approximation that the value of the force of gravity at altitude h is minus gmm over r squared. This is a constant, all right? So the minus g big M over r squared is what we usually call little g. So like this times that works out to about 9.81 meters per second squared. this over here is the error in that, explicitly. And so if you work out the numbers, this 2gmm over r cubed, this piece right here is, let's see here, oh, that's g. This right here is about 3.1 times 10 to the minus 6, your mass times the altitude. So if your mass is a kilogram, let's say, you know, what kind of altitude do you have to get an appreciable error? If you want an error of like 0.1 newtons, or let's see here, maybe I should divide by m. And then if I divide by m, that'll give me the error in terms of the acceleration error. So if I divide by m, then if you think about h being about like 1,000 meters, then you have 3.1 times 10 to the minus 3 error in your acceleration. That's not going to be very noticeable, is it? You're talking about acceleration of 9.8 meters per second squared. If the error is what did I just say? At 1,000 meters, you're just talking about like 0.003. You're not going to notice that. What if you go to 10,000 meters? Then you're talking about 0.3, right? So you're about 0.3 meters per second squared off. Maybe you're still not going to notice it that much, right? What if you go to 100,000 meters? Right? Then you're starting to get to where it's an appreciable percentage. And as you get further out, it gets worse. So at 100,000 meters, the error is about 0.31 meters per second squared. That's about 60 miles, right? And so that's why F equals mg is good to a pretty good approximation even for any of the flight which is possible with planes that the government lets us know about, right? So, okay, anyway, so there you go. That's my spiel on Taylor's theorem. You've been lectured. I'll put this away now unless there's questions. Yeah. Where can you find this? That's a good question. The question is, I want to say that I have put something like this already in your board of blackness. Let's see here.
If it's the old school calculator, it should be on your website.
Yeah, that's also true, but I think I stuck one of these. I feel like I stuck this in here because it came up earlier for something else. Have I not put anything in here yet? Tell you what, I'll stick that PDF in course content for you. Now, I don't know if that really helps you with any of your homework per se, because the homework in the book is actually simpler than like a lot of what I just showed you. Because how do you figure out error in the series approximation for the problems in your homework? They're almost all alternating series. So how do you figure out error there? You don't have to do all this fancy stuff, right? You can just do what? You fall back on the alternating series estimation theorem, you know? So, but if you happen to face a power series which was not alternating in some sense for your question that you're looking at, then Lagrange's form of the remainder is what you have to fall back on. It is a little bit more sophisticated. But anyway, so I'm going to return to calculational techniques. So let's keep chipping away. So we did a few more last class, right? Let's look at another example. How about this? What if I do 1 plus x times 1 minus x, oh, rather, excuse me, I'm sorry, wrong. 1 plus x, and I'm sorry, this is supposed to be 1 minus x. 1 minus x times 1 plus x squared plus x cubed plus dot, 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 dot. Example 2. What if we calculate 1 plus x plus 1/2 x squared plus dot, dot, dot times 1 plus y plus 1/2 y squared plus dot, 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 dot. So for both of these, I want us to try to keep, let's say, to order 4. All right? How do you multiply series is really the question I'm asking you. And so the way we do it is just like you'd expect. So we do order by order. So first of all, what's the constant terms here? There's just one of them, right? 1. Now linear terms. What are possible linear terms? 1 times x, right? Plus what? Minus x times 1, right? Which, if you don't mind, I hate the way that looks. I'm just going to simplify my life a little bit and write that as plus x minus x. Is that okay? How about second order terms? Looks like we got an x squared. Oh, but we got a minus x squared, right? And then we got what? Plus x cubed, minus x cubed, plus x to the 4th, minus x. I think you see where this is going. What's this equal to? Yeah, equal to 1. Is that surprising? Why or not? Cool. I'm just going to zoom in a bit. Buying me some time for people to think. So, explain this to me. Why is it 1? What's this? All right, this is geometric, right? What's my A, what's my R? A equals 1, R equals 2, x, right? So this factor is nothing more than 1 over 1 minus x. So congratulations, 1 minus x times 1 over 1 minus x is 1. Yep, that is true. So it's not surprising our result, is it? No. This one over here, let's work it out. What we got here? We got 1, right? Plus x plus y. What's the next one? You're like, you seem like you're up to no good today. Let's see here, that's probably true. 1/2 x squared, and what else is quadratic here? How about plus xy, right? And then there's also the plus 1/2 y squared, right? Those are all my sort of quadratic terms. And then, well, I think I'll just go that far if you don't mind. Let's just keep up the quadratic and see if we can see the pattern. What's this here? If you tilt your head and squint, you can see that there's a, you can put a 2 here and pull out a half, right? And we'd have what? X plus y quantity squared. Why does this make sense? What's the secret reason that I knew this calculation was going to work out that way? This is part of the power series power series of what? This is what? This is the start of e to the x, right? This over here is e to the y. This over here is the power series for e to the x plus y. So this is not really that surprising. But in fact, you could prove this series calculation carefully, and in so doing, you could prove the laws of exponents. In other words, one way you could do math, is a potential definition. You could say e to the x is equal to the sum n equals 0 to infinity x to the n over n factorial. You could use this for your, this could define the exponential. And with respect to that definition, if you define multiplication of series carefully, then you can prove laws of exponents in this way. So I guess we should define what I mean by careful, right? So what do we mean if we have the sum over, let's say, a sub n, x to the n, n equals 0 to infinity, right? And we're going to multiply that by the sum n equals 0 to infinity, let me say m equals 0 to infinity, of b sub m, x to the m. Well, that should be equal to the sum, let's say k equals 0 to infinity, of c sub k, x to the k. And how do we define, what are the c sub k's defined to be? Here, tell you what, I'm telling you this is the definition of the product of two series, and then you can prove a theorem that says that this actually converges. But how do you actually define these? I mean, what would C0 be? Maybe it helps if I actually write these out. So A0, B0, right? So it seems like that should be the 0th one. How about what's next? How about A1, B0 plus what? A0, B1. That's times x, right? That would be my C1. What comes next? If I had written out more terms, you could see what it was. It would be A2, B0 plus A1, B1 plus A0, B2 x squared, right? So this would be my quote-unquote C2. Can you tell me what the formula is then generically for C sub k in terms of the A's and the B's? I think we're going up to k. And maybe we should say n, whatever letter you like, n equals 0 to k, right? And I want what? I want something like a sub something, b sub something else. So I want the a to range from 0 all the way up to what? All the way up to k, right? So I think I should put an a sub n and a b sub what? I think if I put k minus n, I think that'll be exactly what we're looking for. What is this? That's a0 bk, right? Plus a1 bk minus 1 plus dot 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 plus a sub k b0. That was a 0 here. I think that's the pattern that we've seen already for 0, 1, and 2. Anyway, that is in fact a definition. This is what's called the so-called Cauchy product. Cauchy product of the series. And in fact, you could make this definition for numerical series just the same, and you can prove that the product of two series converges, provided that at least one of them is absolutely convergent. Good news, the power series, if we look at a power series, it is absolutely convergent on the open interval of its convergence. So that means that these will in fact converge, and we can meaningfully multiply power series according to this rule. And you could also use this to define like how to find reciprocal series. Right? Because if you start looking at this, what does it mean to find a reciprocal series? If I have a0 plus a1x plus a2x squared plus, dot, 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 I want to have that times what? Times b0 plus b1x plus b2x squared plus dot, 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 dot. If I want this to be 1 over that series, right? What do I need for this to multiply out to be? What's this need to multiply to? 1, right. So what does that mean? That means you've got a bunch of equations to solve, right? So if you just attack it directly, this would say that a0 times b0 has to be 1, right? It would say that a0b1 plus a1b0 has to be what? 0, right? It would say that a0b2 plus a1b1 plus a2b0 has to be 0, etc. And that's actually kind of an okay way to find inverses if you're just after the first couple terms. It's not too bad to kind of hack your way through this. Here, I'll show you. For example, suppose we want to find 1 over sine x as a power series. So this is 1 over x minus 1/6 x cubed, right? So that's probably a bad idea. Why? I mean, you can immediately see why we get into trouble. If I'm thinking of this as, as this, a0, I'm thinking a0 is 0, right? So if a0 is 0 and I'm trying to solve a0 times b0 equals to 1, that's not good. So what can we do to make this happier, make this example actually be reasonable? How about this? What's the power series for cosine? So here you can see what we have. We have a0 is 1. We've got a1 is minus 1/2. We have a2, I'm sorry, a1 is what? a2 is minus 1/2. What's a1? It's 0, right? And so if you wanted to solve the things you get from the Cauchy product directly, we'd have a couple of equations that we need to solve. First of all, we'd have to solve 1 times b naught equals to 1. So therefore, b naught equals to 1. Well, there's the first term, right? And how about what's the next one? A naught b1 plus a1 b naught equals to 0 tells me what? It tells me what's a naught is 1, right? So this tells me b1, what's a1? Plus 0 equals to 0. So therefore, b1 is 0. Not surprising, 1 over cosine is an even function, so its power series should be what? Should be sum of even powers. So of course the odd term, which is paired with b1, is not there. And let's see here, finally we've got a naught. Let me just write it out here. So that's 1 b2 plus, what was a2? Minus 1/2 b0, what was b0? b0 was 1. Is equal to 0. So that tells me that b2 is what? 1/2, right? So from direct calculation from the Cauchy product, I get that 1 over cosine x is equal to 1 plus 1/2 x squared plus ... So that's one way we could find the reciprocal of a series is by just solving the equations that are suggested by the Cauchy product directly. Now, is there any other way we can find the reciprocal of a series? Is there a better way? There is. How about this? What if we do 1, and we're dividing what into it? 1 minus 1/2 x squared, right? Plus 1 over 24x to the 4th. What happens if I put a 1 here? Then I get 1 minus 1/2 x squared plus 1 over 24x to the 4th. I subtract those. That gives me 1/2 x squared minus 1 over 24x to the 4th. So that I do plus 1/2 x squared. That gives me 1/2 x squared minus 1/4 x to the 4th plus an order 6 term. You take the difference of these, you get 5/24 x to the 4th plus some order 6 term. So then the next term is 5, that's 24. 5/24 x to the 4th. So you see from long division, we've already found that is the power series for 1 over cosine. So in fact, yes, long division, suitably adjusted, makes sense for power series. So we can multiply series. We can even divide them like this. I'll try to do, next time we'll do tangent by dividing sine into cosine or something like that. But anyway, I know I'm out of time, so I'll shut up. So thanks, guys.